Hello, geometry friends. Yesterday we were doing some work in Riemannian geometry, and we were trying to understand this Gauss-Bonnet theorem, which relates the angle to the Gaussian, the curvature, times the surface area integrated over the closed loop. And I define this area here as the volume element, which is the square root of the determinant of the metric, the tensor, times these two, the coordinate infinitesimals, right? And I got a question, which is a good question. Is I don't understand this. I don't understand what this is. I'm paraphrasing the question, but that's what it is, and it's a good question because in my haste to not make a long video, which it looks like I should have, I just blew right through this. I gave you a link to where this comes from, but it didn't explain why it's called the volume element. So let's look at it. All right. So this thing in three dimensions is called the volume element, and you've seen this in calculus 3, but it wasn't obvious. Okay. So back in calculus the 3, you probably saw a volume element dv written as the differentials of the coordinates in Cartesian to space, right? Well, what is the determinant of the metric tensor in Cartesian coordinates? Well, the metric tensor is the identity matrix, so it's 1. So the square root of that is 1. So it was there. It was just 1. Okay, what about the volume element in spherical the coordinates? Do you remember this? Where it was r squared sine the theta dr d theta d phi? Well, what is the metric tensor in spherical coordinates? It's this. What's the determinant of that? R to the 4 sine squared theta. What's the square root of that? R squared sine theta. So it's there. It looks like this. That is this. So tensor calculus, remember, it is the generalization of calculus. It's called absolute differential calculus. That was the first word for tensor the calculus. So that's what makes it so powerful, but it also makes it annoying because you can get lost in the syntax. Okay, in that video, I should have called this the area element because we're working in an area, right? They're just the coordinates here. So it's obviously an area. It's not a volume. But everyone calls this the volume element no matter how you use it. But it really, in this case, it should be called the area element, okay? And we had this expression, which was the determinant, the square root of the determinant of the surface, the coordinates, which is just this piece, right, was r squared sine theta. All right. So let's integrate just this. And I had my point, and we're going to go look at the graphics in a moment, at 45 degrees, which is a pi over 4. And the phi went all the way around, 0 to 2 pi. So the theta came from 0 to 45 degrees, and the phi went all the way around. So we integrate that out. We get this. And so the area of what we're getting ready to look at was 1.84. So let's go look at it. Okay, so here's how we started. So we have a unit sphere. So the radius is equal to 1. We put a point on it. We brought the theta, which just goes from the North Pole down to the equator. We set it at 45 degrees. We set the phi, which goes around the equator, like that. We set it at 0. And we plotted a vector. So this is a unit tangent to vector at that point. And we said, what happens when we parallel transport that vector all the way around the circle? It comes back here, and it's like totally different than it was. And it's pointing in a totally different direction. So we took a snapshot of that at the beginning and the end, and we used that Gauss-Bonnet, the theorem, to calculate this angle, right? But now we're talking about the area, right? So let's get those vectors off there. Boom, boom. And what we want to do is take oh boy, I got a lot of stuff on here, don't I? we want to take a slice right through that sphere at that point. And you see that defines a circle around there. And we want to know, what is the area of this cap? What is that area? Because that's what we were working in when we did the Gauss-Bonnet theorem, right? Okay, so let me get the sphere off there because it gums up everything. And let's turn this around like this so we can look at it. And now, you remember from geometry, wherever that is taught, that the area of this cap here, sliced by this plane, is going to be 2 pi times the radius times this little height, h, right? So you say, well, what is that little height, h? Well, we have to find it. And since I got vectors on the brain, that's the only way I know how to do it. So I defined a vector from the origin to this plane, okay? And you see that's how tall it is. That's the magnitude of that vector. Well, then this piece left over must be 1 minus that, right? So it's 1 minus that. So it's this, the number here. So this is our h. So if we say 2 pi times our radius is 1, times that little piece, we get that 1.84, which is exactly the same number we got back on our document. So let's go look at that. Okay, so here's what we got in integrating the volume element. Here I go again, the area element. And here's what we got by the geometry, the method, one plus. So it's the same area, okay? So I hope that cleared that up. I should have spent the time in doing that better, but we got it done. All right, I'll see you later.